Yeah, so today I'm going to give an overview of pseudorandom codes that will include 3 of my papers. All of them are with Sam Gunn, who's a PhD student at Berkeley. And then the second paper is also with Omar, Prabhanjan, and Yevgeny. The third paper is with Noah, Ankur, and Daniel. And so, yeah, I think it's ambitious to fit all 3 of these papers in. We'll see how far I get. But hopefully by the end of the talk, I want you all to know what a pseudorandom code is and have a sense of why they're useful for watermarking. OK. So what is a pseudorandom code? You can think of it as pseudorandom encryption combined with an error-correcting code. You'll see this in more detail later. And why do we care about pseudorandom codes? Well, the main application is for watermarking AI-generated content. So imagine you're given a piece of content, maybe some text or an image, and you want to know whether it was written by a human or generated by AI. So you've probably seen this problem a lot. Like now, a lot of the content that you encounter on the internet is AI generated. And a natural first attempt at solving this problem is to train a classifier, an ML model, to distinguish between these 2 things. And there are lots of classifiers that are actually publicly available that do exactly this, but they have some issues. So one issue is that if you ask ChatGPT really nicely to evade detection by these classifiers, it actually manages to do so. And on the other hand, one of these classifiers is pretty convinced that the US Constitution is AI generated. So it's like 90-something% confident that the Constitution was entirely written by AI. This is funny, but there have been some real-world consequences of these detectors' unreliability. Like real students have been falsely accused of plagiarism because of these faulty detectors. And these false positives are more prevalent among non-native English writers. And so as a result of these issues, a lot of organizations are moving away from using these AI-based classifiers that we don't understand so well. And I think the problem with these is fundamental. Like the problem with training a classifier is that all it has to work with are sort of existing markers of AI-generated content. And as we train these models to become better and better, we're explicitly trying to make their content look more human-generated. And so we're actually removing these markers. The idea behind watermarks is instead of having to rely on markers that are already there, we are going to actually change the content to embed these markers ourselves and hopefully have more control. OK. And so today I'm going to present, not in great detail, but I will show you a framework for a watermarking scheme that basically considers any generative algorithm that is highly randomized. So this will work for any algorithm that takes, in addition to its prompt, some randomness and uses the randomness and prompt together to compute some content. And this is the way that most generative models work, right? Like if you ask ChatGPT to write an essay on some topic, if you ask the same prompt many times, it'll write lots of different essays for you. So the generative models that we have in practice are highly randomized. The same is true for image models. And so this framework actually does work for practical algorithms. And the properties that we'll want of the watermark are, first, we will want the quality of the model to be preserved. So we don't want to be making ChatGPT output worse essays because we're adding the watermark. We also want the watermark to actually be detectable. And furthermore, we'll want to still detect the watermark even if someone comes along and modifies the content. So if we have a watermarked essay, even if many of the words are changed, the watermark should still be there. This is called robustness. And then finally, we'll want a provably low rate of false positives. We'll actually ask for this to be negligible. OK, and by the way, please feel free to ask questions at any point. OK, so what a watermarking scheme gives us is, like a generative model, it allows users to input prompts and get back some content. We want this content to be watermarked. And now the watermarked model will use some secret key, SK, to generate this watermarked content. In addition to the secret key, it'll use some neural network, M, to create this content. OK, so from the user side, the functionality looks the same. You query prompts, and you get back some content. Then a watermarking scheme also offers a detection algorithm, which uses a secret key as well. And you can query this detector with any content, and the algorithm will output true or false, indicating whether the watermark is there. OK. And so like really fast crash course on how we'll build watermarks is we're basically going to we're going to take advantage of the fact that these generative algorithms use a lot of randomness. And in particular, these models have the property that there's some approximate randomness recovery algorithm that takes content generated by the model and approximately recovers the random string that was used to generate it. And this should be extremely surprising. There's like on the surface, there's no reason why we would expect this approximate randomness recovery to exist, but it actually does for LLMs and for image models. And I don't have time to go into detail about it during this talk, but if there's time at the end, I can talk about it a bit more. But all you need to know about this algorithm is that it takes as input some content, and it outputs a string that is close in Hamming distance to the random binary string that was used to generate it.
Sorry, I blanked for a moment. So this is something that already exists in existing generative systems.
Mm-hmm.
So this is like something you take as a given in the SQL.
Yeah. Yeah, so you should all take this as a given. In our first paper, we had to prove that this algorithm exists for LLMs. And so, yeah, we actually had to show that it exists, but it does. Yeah. And I guess maybe reason to believe that it exists is these generative models are so randomized. Like ChatGPT can write so many different essays that the randomness has a huge influence in the content that's produced. So, yeah.
So if you actually showed it in your paper, why aren't you citing it in this slide?
Oh. OK. See gun 24.
Yes, awesome. OK.
Yeah. OK. And so if you believe me that this approximate randomness recovery exists, then a way that you can construct a watermark is to take the binary random string used by the model, replace it with a pseudorandom code word, which will come from a pseudorandom code, and now just use the generative model as before to get some content. So here we're replacing true randomness with pseudorandomness. So this should not affect the quality of the content that's produced, because you can't distinguish between pseudorandom and random. And now,
sorry, I had a question. So that algorithm requires this model, knowledge of this model, all the parameters.
good question. For LLMs, it does not require any knowledge of the model. It's basically like you take your text and you convert it to binary.
Oh, you don't even need to know this? Like everybody can?
Yeah. Yeah, it's not dependent on the model at all. For image models, you do need to know the model used. Yeah. And so what pseudorandomness gets us is the watermark is what's called undetectable, which guarantees that the quality of the content is preserved. And what error correction gets us is that now, by taking some content, running approximate randomness recovery, we get something that's close to the pseudorandom code word used to generate it. And if we have some robust decoding algorithm, then we can still recover whatever message was used to derive this code word, which in our case, we'll just need to encode messages of 1 indicating the watermark, or like 0 or bot indicating nothing. Yeah. OK, I just threw a lot of information at you. This is all I'll say about the actual watermarking scheme, so it's a good time for questions.
So what happens if the content is modified? Like there needs to be some guarantee about how close the randomness you recover is.
Good question. Yeah, so for text, randomness recovery is just taking each word and converting it to binary. And so there's like a really nice mapping between words that are changed and bits of the code word that are changed. Like if you change a word, you're just changing the bits that that word corresponds to. So yeah, you can prove a nice relationship for LLMs between the number of words that are changed and how randomness recovery is affected. For image models, it's a little bit different.
This question was okay, I already forgot, sorry.
Wait, how do I see it?
Does robustness hold if you feed it to another LLM?
Yeah.
Oh, so, oh, nice. It depends what you ask the other LLM to do. If you ask the LLM to like completely paraphrase and change every single word, then this watermark will be removed. So the kinds of watermarks for text that I'll talk about today withstand edits. So you can change words, insert words, and delete words. But if you arbitrarily paraphrase, then the watermark is removed. So a good direction for future work is semantically robust LLM watermarks, which persist as long as the meaning of the text is not changed. And there aren't really any schemes with provable guarantees there.
But then if you feed it to another LLM, if that one's more than watermark, that's
Then you're
fine.
good.
Yeah.
Yeah. But I guess in general, you would hope that even if you feed it to some like malicious LLM, as long as it keeps the meaning, then the watermark should still be there.
Question. Do you need the prompt to do this randomness recovery?
No, you don't. So you just have some mapping from words to binary strings. Say you like take each character and write it in binary. For text, the randomness recovery is exactly that. You just take the words and you map them to binary according to this fixed mapping.
And you can get the code word out of that?
Yeah.
Oh, okay. What if there's like multiple prompts that result in the same content? So they would go back to the same code word?
That's okay.
Okay.
Yeah.
So based on the way you're describing this seems to be the case, but just to confirm, like, this is somehow like an insertion deletion code where if I like delete a word and otherwise and just like shift all of my words over, somehow I'm still robust to this and it can still be code?
Yeah. So we do construct codes that are robust to edits, insertions and deletions. In this talk, I'll only focus on codes that are robust to substitutions, just because it's easier to think about. But yeah, we use Reed-Solomon codes and have some modifications that let you tolerate insertions and deletions as well. But I won't go into detail about it at all today. Yeah.
I guess I remember hearing another talk on this where they were talking about like the entropy of the prompt. Like certain questions have like only one right answer, and an LLM is only going to output like most of the time is going to output that one answer. So like that's a prompt that you like can't really watermark. Is that kind of the same thing here, and you're just like glossing over it, or is that?
Yeah, good question. I'm very much glossing over it. So one question you might ask here is how much error is introduced in approximate randomness recovery. And it turns out that you can like very precisely relate the amount of error introduced to the amount of entropy induced in the response given the prompt. So for prompts that only have one correct response, the error rate will be like 1. And yeah, in the paper, we like prove a bound on the amount of error introduced based on how much entropy is given by the prompt.
So really good for watermarking like English essays, and not so good for watermarking like implement quicksort or something.
Yeah, in general, it's much harder to watermark code because like the entropy is, there's like high entropy in certain tokens, and then you'll have like very long chunks of code that have 0 entropy.
Sorry, just with the approximate randomness recovery, like if you are feeding into that something that like a human made, I'm assuming like this like relies on the assumption that any piece of content theoretically could be generated by like an LLM with a given randomness string and a given prompt.
Are you asking about falsely flagging human-generated content as watermark?
I'm saying like when you talk about that approximate randomness recovery, like you're saying, okay, we're gonna feed into it this piece of content that was generated by an LLM, and it'll give us back a random string that's like close in Hamming distance to the original random string. But like if you feed it something that isn't generated by AI, it's still gonna give you an output, right?
Yeah.
So I'm saying like you're kind of inherently making the assumption that that thing like any piece of content that you feed into it theoretically could have been generated by AI with a given prompt and a given random.
So what you'll get back if you feed a human-generated text into approximate randomness recovery is you'll get some binary string that's far in Hamming distance from everything in the code.
Okay.
So every text can be mapped to a binary string.
Right.
If the text didn't come from the watermarked LLM, then this string will be unrelated to the code.
Okay.
And so the detector will output false.
Does this work the same way for like images, but instead of words, we focus on like pixels in the image? Or how would that work for images?
Yeah, so for images, it turns out that the way these image models work is they first sample a random vector that determines the higher order features of the image, and then they map that to something that consists of pixels. So here, randomness recovery takes the pixels and maps it back to this feature vector. So it's quite different. Okay, I'm going to move on to the pseudorandom codes. I think this probably leaves a lot of questions about watermarking, but that's like a whole talk on its own. So, okay. Okay, so I showed you this at the beginning. Pseudorandom codes are pseudorandom encryption and error correcting codes. And in a bit more detail, what this means is that if you have an encryption oracle, this is computationally indistinguishable from the uniform distribution. So you can ask the oracle to encrypt even the same message over and over again, and all of these ciphertexts should be indistinguishable from random strings. What error correction means is that if you get some ciphertext and you add some low-weight error, so you should think of ciphertext as binary, and the low-weight error being like flip each bit with probability 1/3, then you should still be able to decrypt and recover the message. So in particular, we're thinking about a constant rate of bit flips. Okay, and just visualizing what ciphertexts look like, say these are all encryptions of 1, they should look like random binary strings. And what error correction says is that if you take Hamming balls around any of these strings, then everything in these balls should still decrypt to 1. Okay, and so the first few works constructing pseudorandom codes showed that if you represent strings that decrypt incorrectly as red dots, so all of these red dots decrypt to 0 instead of 1, then the density of these red dots within the Hamming ball is negligible. So this says if you take an encryption of 1 and then add random noise, you're unlikely to reach a string that decrypts incorrectly. And what this kind of corresponds to is if you get some watermarked content and add random noise to it, then it'll still be watermarked. But this is a bit unsatisfactory because in practice, like if someone's trying to remove the watermark, they're not going to add random noise. They can make more like clever changes than that. And so, yeah, just to reiterate the kind of guarantee that we got from sort of the first wave of pseudorandom codes is if you add errors independently of the secret key, then you're unlikely to reach one of these red dots. And so sort of the watermark is robust to errors that are made independently of the watermarking secret key. Okay, and now I'll show you why this kind of weaker guarantee arose. So the first pseudorandom code construction was from Crypto 2024, and it was based on learning parodies with noise. So you can think of LPN as saying that if you have a bunch of noisy code words from a random linear code, then these are pseudorandom. Right? So if you have a generator matrix G, then a bunch of strings of the form GS plus E are pseudorandom. And so if we sort of think about trying to construct a pseudorandom code from LPN, I think a natural thing to do would be to say, if we want to encode the message 0, output a random string. If we want to encode the message 1, then we output a noisy code word. So this is pseudorandom exactly by LPN. Right? The encryptions of 0 are just random. The encryptions of 1 are noisy code words, which are pseudorandom by LPN. But also by LPN, this is not efficiently decodable. Because LPN says exactly that even if you know G, you still can't tell the difference between noisy code words and uniformly random strings. And so to tell whether the message was 0 or 1, we need to do exactly that. And so the main insight between our first construction was just to sample the generator matrix G along with a trapdoor that lets us efficiently distinguish between random strings and noisy code words. Okay. And so what the trapdoor is it is a sparse matrix H. So there are few ones in each row. And then we just sample the generator matrix subject to the constraint that H times the generator matrix is all zeros. And the reason why this trapdoor is useful is that if we have a noisy code word, GS plus E, and we multiply it by H, then what we get is H times E. And if H has few ones in each row, and E is also some sparse error, then H times E will have very low weight. Whereas we'd expect that H times a random string would have weight like close to 1/2 times the length of the string. So by multiplying some string by H, we can tell whether it's a noisy code word or unrelated to the code.
So based on the pseudo-randomness argument, I would assume finding H given a G such that H equals 0 has to be a difficult problem as well?
Exactly, yeah. So pseudo-randomness implies that it's computationally infeasible to find such an H if you're just given a random G. Yeah. So importantly here, we're sampling H first, and then sampling G subject to matching that H.
Isn't that totally not the direction that I expected you to go? I expected you to make S secret and reuse it all the time. Is there a reason that you're doing it? Does it like degrade the quality of the LPN or something?
I guess how.
Only get quadratic expansion for primal LPN if you fix the S.
Oh, because eventually you will learn.
Yeah, yeah.
Okay.
Oh.
Yeah, I think that's one issue. And another question was, like, is this a standard LPN, or is this part information theoretic, or it relies on another assumption, or like a stronger version of LPN?
Good question. So to show that G sampled using this procedure is actually random, you need to take G to be really skinny. So G can only have log squared security parameter, many columns.
Okay.
And so this means that when you show that GS plus E is pseudorandom, you need sub-exponential LPN. So here, G is statistically random if it's skinny enough. And then noisy code words generated from G are pseudorandom under sub-exponential LPN.
I see. But then every time you would freshly generate some S.
Yeah.
The same skinny G.
Yeah, so you keep G, that's like your public key. H is your secret key. Actually, here. H is your secret key. G is your public key. And then each time you want to compute a ciphertext, if you're encoding 1, you draw fresh S and fresh low-weight error E. You output GS plus E. If you want to encode 0, you sample a fresh uniform string. And now to decode, you take whatever you want to decode, you multiply by H. If it was a noisy code word, then this has low weight. If it was unrelated to the code, then this will have high weight. Okay, and so what we were able to prove is that if there's some error E prime that is independent of the parity check matrix H, then H times the ciphertext plus this error E prime will have low weight. So this is why we get the guarantee that like if you have error made independently of the secret key, then it's unlikely to cause incorrect decryption. But if you actually know H, then it's easy to find E prime that causes this to be high weight. And so this is kind of a weak form of robustness. Yeah, so we proved this only over choice of H. So the way that we proved robustness is we considered someone who chooses E prime, and then H is chosen after. And so, okay, I've spent a lot of time complaining about the robustness of this, of CG24. The question we asked in the follow-up paper, Ideal Pseudorandom Codes, is whether it's possible to construct a scheme so that the red dots are actually hard to find. Like, not only is their density negligible, it's actually infeasible for the adversary to find one of the red dots within this blue ball.
Even if you know it's a secret key?
We're getting there,
Okay.
yeah. So eventually that would be great, but for now, we're just going to ask that an adversary that has encoding and decoding oracles can't find a red dot. So yeah, we call this object an ideal PRC, and I will define it in a minute. So yeah, the red dots will still exist, but we're going to show that it's hard to find them.
So the initial pseudorandom definition, is it more like CPA style, and this is more CCA style? Or maybe the initial definition doesn't even have this goal of finding the red dots.
Yeah, so the initial definition is like CPA pseudorandomness, but that says nothing about robustness. The new definition will be like CCA security.
Okay. But there's also this additional piece where the adversary tries to find an encryption, a valid encryption of 0, whereas the original definition is not.
Yeah. So, okay, maybe the simplest way to say it is the original definition of robustness considers an adversary that cannot interact with the code at all. The adversary chooses its error before seeing any information about the code, or in the setting of watermarks, before seeing any watermarked content or querying a detector.
Oh, I see.
Yeah. So this ideal PRC will capture an adversary that can see watermarked content and query a watermark detector, and then try to remove the watermark.
I see.
Okay. Yeah, so now I'll talk about this definition with improved robustness called ideal pseudorandom codes, and this was at Stock last year. So what an ideal pseudorandom code is it is a pseudorandom code where the actual encoding and decoding oracles are computationally indistinguishable from ideal encoding and decoding oracles. And what these ideal oracles do is when you query the encoder with some message X, it'll respond with just a uniformly random string, which you can think of as the code word encoding X. And yeah, you can query the encoding oracle with as many different strings X as you want. What the decoding oracle does is when you query some string C prime, it'll look at all of the C's that the encoder previously output and see if any of them are close to the given C prime. If so, it outputs the corresponding message. So you can think of the ideal encoder and decoder as implementing just a random code. So code words are random strings, and you decode by looking at whether the given string is close to any of these random code words and outputting the corresponding message. Okay, and so this definition captures both robustness and pseudorandomness, right? This code is like perfectly robust because you're exactly checking whether the queried string is close to any code word and outputting the corresponding message if so. It's also pseudorandom because the code words are actually just random strings. Any questions about the definition? Okay. And so what we showed in this paper is that these ideal pseudorandom codes exist assuming sub-exponential LPN.
Sorry, maybe this is a silly question, but I don't understand how you're supposed to be guaranteeing robustness if you're like literally outputting a uniformly random code word for anything that you're inputting and trying to encrypt. Like,
Yeah, so robustness is guaranteed because these two algorithms are stateful. And so when you query a string to the decoder, it checks whether that string is close to any of these random code words that the encoder output. If so, it returns that message.
So the outgoing error that says uniform C though, like in what sense is C uniform?
So
like, it's,
there's two things. This is an oracle that mimics the ideal code. As in, the adversary cannot tell, is he talking to this ideal oracle or to the actual code that runs the algorithm?
I see.
Yeah, so I'm describing a code that is completely inefficient. Each time you query the code word, each time you query the encoder, it samples a uniformly random string and adds that to the codebook. The decoder will look at the whole codebook, check whether any string is close to the given one, and if so, return the message that was used to form that code word. So it's robust like by definition.
But I guess, so what's confusing to me is like the sense of close is necessarily dependent on how tightly packed like the uniformly random things that you've added to your codebook are. And if you click get unlucky and there are two things that are right next to each other, and then you try to decode something which is very close to both of those, I don't understand.
Okay, good question. So yeah, you only get robustness if you're limited to a polynomial number of queries. Yeah. Yeah, so yeah, that's a good point. As long as you encode at most a polynomial number of messages, then you will never, with overwhelming probability, you will never output two code words that are close together.
So the adversary wins if they can distinguish between the two.
Exactly.
And it implies that the adversary cannot find a valid red dot because then it would be like finding this decoding, like C prime would be a valid red dot, which will just return bot in the ideal world.
Yeah, exactly. So if the adversary can, find a red dot, then it can query something close to that red dot, which will be blue, and then observe that it's found two strings that decode differently. Yeah. Okay. And so what we showed in this paper is that these ideal PRCs actually exist. And this is essentially just by better analysis of that construction that I already showed you. So the first step in our analysis is showing that that construction already satisfies sort of an intermediate notion of idealness, where the adversary can only query an encoding oracle. So yeah, we show that it's hard for an adversary that queries the encoder to find any of these red dots with the construction that we already had. Then step 2 in the proof is we give a generic compiler that takes any encoder-only ideal scheme and transforms it into a fully ideal scheme, and this is only using a PRF. So putting all of this together, we're able to come up with an ideal PRC under exactly the same assumption as the original construction. Okay. Where did my mouse go? Okay, I'm just thinking about time. I'm going to skip the proof for now, but if there's time at the end, I can talk about the step 1 where we show that the construction is already encoder-only ideal. Okay. Oops. So just to reiterate why we wanted this ideal PRC in the first place, is what it gets us is it says that the resulting watermark is robust even to an adversary that can see previous watermarked responses, so we can query watermark ChatGPT freely, and also query a detector for the watermark. And this is kind of the practical kind of robustness that we would want. Okay. But you might ask whether it's possible to show that there aren't any red dots at all. And so that is one of the questions that we answer in this newer work, which will be at Stock this year, called Improved Pseudorandom Codes. And what we do in this paper is we give a completely new construction of pseudorandom codes from something called the permuted codes assumption that I will show you. And these pseudorandom codes have several different improvements. The first one is it's the first construction that has plausible sub-exponential security. So one kind of downside of all previous constructions is there were known quasi-polynomial time attacks. So in particular, for the construction I showed you, there were these log sparse parity checks, and you could find them by brute force searching over all n to the log n possible parity checks, and this would let you learn the secret key, which is not so good. And so this was actually a bad feature of all existing constructions, and it wasn't clear whether sub-exponential security was possible at all. And so that was kind of my motivation behind this paper, but we ended up getting some other nice properties as well. So the second property we got is worst case robustness, meaning that the red dots do not exist at all. So every single string within these Hamming balls decrypts correctly. And then a third improvement that we got is we're also able to tolerate edits. So an adversary can not just change words, but also insert and delete words, and the watermark still remains. And so maybe the reason why I showed ideal pseudorandom codes as well is my feeling is kind of that this new construction is incomparable to the old one because it's based on this permuted codes assumption that's highly non-standard. So the ideal pseudorandom codes had sort of weaker properties, but it was based on sub-exponential LPN, which I feel is standard. But this new construction is based on this permuted codes assumption. But it's not a totally crazy assumption. It was actually, or it's related to a different assumption that was introduced to construct doubly efficient private information retrieval, which maybe only cryptographers know about. But it's not a completely new assumption, and ours is implied by this existing one. Okay, so yeah, to reiterate, before we had that red dots are hard to find, and now we'll remove the red dots entirely. We'll have a worst case kind of robustness. And furthermore, we will be able to take these to not just be Hamming balls, to be balls in terms of edit distance. Okay. And so I'll spend the rest of the talk showing you this permuted codes assumption, which I think is pretty interesting in its own right. And I think like if you don't know doubly efficient private information retrieval, it's extremely hard to construct. There are basically only two constructions, and one of them is from this permuted codes assumption. And my feeling is that there are lots more things we could do with it, so I really want to highlight it today. Okay. And so what the assumption will say at a high level is that for an appropriately chosen code, any polynomial number of noisy and permuted code words are pseudorandom. So I'll show you more specifically, but what is kind of different here from LPN is that LPN, you need to consider just a random linear code. Here, you'll be able to consider a much broader class of codes, which is nice. You can have more structure. But you'll have to sort of infuse hardness by not just adding noise, by also permuting as well. And so for this assumption, the first thing we will need is a linear code C over an alphabet sigma that has polynomial dual distance. So one way of thinking of this dual distance is if you take a random code word, if the dual distance is like K or T, K, if the dual distance is K, then random code words are K-wise independent. So if you restrict your view to K of the symbols, then these are actually uniform. And so this dual distance requirement will be important for getting pseudorandomness because it says sort of there aren't any small correlations between the bits of the code words or the symbols of the code words. Okay, so we'll need this linear code with this restriction on the dual distance, but that is the only requirement that we'll have on the code itself. Then we will also need a bunch of random permutations over the alphabet. So for each index of the code word symbols, we will have a different permutation, pi. And then finally, we'll have a sort of index-wise permutation sigma that is over 1 through n.
Sorry, the K-wise independence is over like a uniformly random code word, assuming you're like encoding a uniformly random input, or what is the randomness?
Draw a random code word from the set of all code words. Yeah.
Sorry, how can it have poly-n dual distance if the length is just n?
Small poly, like n to the epsilon.
Oh,
Yeah, like square root n.
I see. Oh, I see. Thank you.
Okay. And so what the permuted codes assumption says is that if you take a random code word from C, so you take your set of all code words and you pick one at random, now you apply the alphabet permutation to each symbol of the code word. So, for the first symbol, you permute by pi 1, and this outputs a different symbol in the alphabet. You do the same for each of them. now you add a constant rate of noise. So say with probability 1/3, you replace each symbol with a random symbol from the alphabet. And now finally, you move the symbols around according to the index-wise permutation. Right, so if little sigma of 1 is equal to 2, then in the first index, we will put the second block. Okay. And so what the permuted code's assumption says is just that any polynomial number of noisy permuted code words sampled this way are pseudorandom.
So this is how it improves on my idea, you can just reuse S, is that if you reuse S, you can solve LPN, but with this added permutations of the LPN is hard. I don't know.
Maybe.
Maybe that doesn't make sense.
I never think about S.
It's okay.
No, here you still can't reuse S because you're choosing a random code word each time. So this is like you're choosing, for each of these, you're choosing a random S and then still adding noise and permuting. So this is kind of like if you take a random linear code as C, then this is the same as LPN with further permutations.
Right.
So for a random linear code, this is implied by LPN. So this is like you're doing even more to scramble the code words, but we're conjecturing that this is pseudorandom even if you start with a fairly structured code. Other questions about the assumption?
So I think it's really tied to, like it seems the assumption is really tied to resolve one code. Like, do you know if it's also for a broader family of code?
How is it tied to Reed-Solomon codes?
I think because mainly resolve one code. And so you choose the roots of unity to evaluate beforehand. And so you evaluate the polynomial on this root of unity. Now when you shuffle them, you don't know the root of unity to interpolate anymore. So that's why it looks random now. So is this do you know if this assumption is true? Is thought to be true for other kind of courses as well?
Yeah, so okay. The Reed-Solomon codes are interesting because it's actually the code that I'm least confident this assumption holds for, which also happens to be the code that we use for our construction. But we do show in the paper that if you omit the pi's, then Reed-Solomon codes, the assumption is false for Reed-Solomon codes with the pi's omitted. So to me, Reed-Solomon codes feel very risky. I conjecture that this holds for any code with high dual distance. So I think in the paper we talk about algebraic geometry codes. Yeah.
Thank you.
Okay. Yeah, and so if you're familiar with the doubly efficient private information retrieval constructions, several of them use the permuted puzzles conjecture, and that is the one that implies permuted codes. And they also conjecture it for Reed-Solomon codes. Yeah. Okay. You might be wondering why this assumption is useful. It very naturally gives us an encryption scheme where the secret key consists of these secret permutations, pi and sigma, right? So if you know the permutations, then you can unpermute and decode. Meaning if you have one of these code words, first you use sigma to put the symbols back in their places, and then you use the pi's to reverse the alphabet-wise permutation and get back the symbols of the actual code word. Okay. So maybe the last couple minutes, would people rather see more pseudorandom codes or watermarking open questions? Open questions? Okay. Pseudorandom codes? Maybe I'll do pseudorandom code open questions. So I guess the main issue right now with using pseudorandom codes in practical LLM watermarks is that sort of the error added by randomness recovery is quite high. And what this translates to is you need very long code words to recover from this error. And so what that means for watermarks is you need many words to embed the watermark. So right now, if you implement a watermark with like the pseudorandom codes that we have, you basically need an essay's worth to detect. Yeah. So I think a technical question here is whether we can come up with a new construction that has a better concrete trade-off between the error tolerance and the length of the code word. And sort of the problem with existing constructions is you have these log n sparse parity checks, and it's sort of like it's hard to say much succinctly, but I think we really need a new construction that has a better trade-off between the length of the code word and the error tolerance. And so this is a nice, maybe like coding theory question, and I think combined with the permuted codes assumption, which works for any code with high dual distance, this might boil down to just finding a favorable code. Another thing that would help with this is nobody has studied the randomness recovery algorithm for LLMs further than we did in our first paper. And for that, we just wanted like a pretty simple description. And so we went with the first algorithm we could think of, and nobody has improved it since then. So I think there's probably some low-hanging fruit in terms of the randomness recovery algorithm that we use to go from text and map it back to the binary string that was used to generate it.
What's the sense of improvement you're hoping for? Like how close you are to the original random string or the runtime?
Oh yeah, in terms of the error in approximate randomness recovery. So right now, what we do is we, I think, take each, we have some mapping from tokens to binary strings, and we just fix that mapping and use it. That results in a lot of error because I guess if you have, say, a single token in the response that is entirely deterministic, then you can't hope that you embed the actual code word bits in that token. And since we have this mapping from tokens to many bits, this results in many errors. Whereas you could try to only extract one bit from each token, and then you would need like less entropy in that token to get that one bit embedded correctly. Whereas right now we're asking for concretely, I don't know, like something like 10 bits per token, and you really just don't have that much entropy in each token. So I think a simple way you could improve our randomness recovery is just by embedding each bit in the hash of a token instead of trying to embed like 10 bits in each token. let's see. And then maybe okay, 1 minute. I'll highlight my favorite result about pseudorandom codes, which is this last. Actually, these two papers collided and showed the same result with the same cool proof technique. And they shared the Outstanding Paper Award at TCC last year. And they were able to show that pseudorandom codes cannot be black box constructed from one-way functions. So this means that there's no generic construction of pseudorandom codes from one-way functions or like pseudorandom functions, secret key encryption, and then they further strengthened this to include virtual black box obfuscation and public key encryption as well. And they proved this using hypercontractivity, which is kind of cool. Question?
Yeah, I was just, I'm just wondering, like, what are the, like, incentives for the people making the LLMs themselves to include these watermarks in that? Like, do you have plans to try to get this, like, accompanied by some sort of legislation? Because otherwise, like, I feel like the LLMs are just incentivized not to do this.
Yeah, so currently Google has already deployed an LLM watermark.
Okay.
Many companies have deployed image watermarks. Google, Amazon, Meta. And this is because there's already legislation.
Okay.
So legislation has already been passed, but I think none of it has gone into effect yet, but it mandates that watermarks must be added.
Okay.
Yeah.
Sorry, this is kind of a follow-up. If I recall correctly, I believe like there's, for example, synth ID for Gemini generated images, and for most mainstream LLMs, there's watermarks for images. And I'm wondering, you said that image watermark and text watermark is very different. So what's so different about them that image watermarks are already like in use and text watermarks are not quite like production ready?
Yeah, I think the main difference is that there's a lot more randomness in in images. So right now, LLM watermarks are limited by low entropy tokens. Like that's what causes our watermark to require so much text. For images, there is just like a lot more randomness, right? You can have even images that look the same to a human, but have different pixel representations. And so it's really a difference in entropy in the content that makes images much easier to watermark than text.
I have a question.
Yeah, Victor?
Yes. So maybe you already went over this, but I was just wondering, in case LM become as good as humans in terms of text generations, will that imply that it will be possible for a human reading text to be mapped back to a pseudorandom code, or will the security of pseudorandom code prevent that?
Yeah, so the soundness property of pseudorandom codes implies that any content that is generated independently from the secret key will map to something far from any code word. So regardless of the ability of the model, if something was generated without using the secret key, then it will not be detected as watermarked.
Okay, thank you.
So yeah, I guess I'm also curious. So it seems good to watermark content with like a binary value saying this is LLM generated content. It seems really like potentially dangerous to enable watermarking because you can consider like watermarking it with the specific user's like name and like the current time and other information, and then they're just completely unaware of the fact that their content is tagged with that. And I also like, is there any way that you could guarantee to users that you have not watermarked their LLM output without like them knowing like the model weights and stuff like that?
No. Yeah, so one thing that's interesting is the legislation that mandates watermarks also mandates that a lot of that metadata is added as well. So
that's
like
terrifying.
not user ID, but things like time, model version, I don't remember what else.
Okay.
Yeah, and when I read that too, I was like, oh, that if users don't know about that, then you're kind of accidentally putting a timestamp on, say, the prompt that you use to generate some content.
Yeah, or you could even leak information about the prompt, which could, have like secret, like stuff the person doesn't want to share with people who just look at the output of the LLM or something
Yeah.
like that.
Yeah.
So I don't like really know what the alternative is to what you're doing, but I'm just trying to think of like what reasonable attacks on something look like here. So like if I ask ChatGPT to write me an essay but write it backwards and then I just reorder it from front to back, presumably the edit distance is now very large from what I had, and like this reason I just have it and I swap them doesn't clearly have small edit distance.
Yeah.
And so I guess like I'm not sure it's a question, but like I guess the question is like, what about stuff like this? Like it feels like if all you're doing is providing guarantees as long as the edit distance is small, they're pretty straightforward ways of soliciting the response that you want from LLMs.
That is true. So, okay, yeah, we prove robustness to edits, but a lot of these constructions are also robust to like reordering.
Okay.
That one is easy, but in general, a problem with watermarks is if an adversary looks at the scheme being used, then it's pretty easy to come up with some kind of edit that isn't covered by that scheme's robustness. And really, my motivation for robustness isn't against a dedicated attacker because kind of in the limit, they can always use an unwatermarked model. And I don't think there's anything we can do to prevent that. But I think robustness is still important just like to get a sense of what content is out there. Like if you have a lot of users just honestly interacting with a model and then posting this content online, they're not trying to remove the watermark. It's still useful to know that this was AI generated. And most users won't go and post the content unmodified. Like just, you don't like some words, you maybe edit the image a little bit, and then you post it. And so robustness is useful even when there's no attacker and they're just like honest users modifying the content. Okay, I think we're over time, so if anyone needs to leave, that's fine. But I'm happy to keep answering questions if there are more.
I think that's